Today we're going to be introducing more symbols that we can work with in the world of logic. These symbols are pretty similar to the not function that we are used to seeing already. So we attach a not function in front of a statement, say px, in order to show that this is the opposite of what px really means. And what I want to show you now are two new symbols that are pretty similar to the not function, in which you attach them in front of the statement in order to clarify a bit more about that statement that you're dealing with. So the first one is something that looks like this, and the second one looks like this. Okay, so what does this mean when we attach a symbol like this in front of px? This means that for all mathematical objects or all values of x, the statement px is true. So as an example, let's give and assign a meaning to px. We're going to give it the meaning x is greater than 0. So this would mean for all values of x, x is greater than 0. And this may or may not be true depending on the universe of discourse. Remember, this is the universe in which our mathematical objects come from. This is the warehouse, if we're still using that same analogy. So if our warehouse is filled with positive numbers like 1, 2, or pi or something like that, then this statement is of course true, because if you pick any mathematical object x from the universe of discourse, then it's all going to be greater than 0 because it's filled with positive numbers. On the other hand, if our universe of discourse also happens to include negative numbers, then this statement would be false because we have negative numbers and they are not greater than 0, so you can't say that. So this highly depends on context. So context matters a lot and you should keep that in mind. Okay, so what about this guy over here? What does it mean when we attach this symbol in front of px? This means that there exists at least one mathematical object that satisfies px. So if we use the previous example, our universe of discourse, say, includes both negative and positive numbers, so -1, -2, 3, like that, then this statement would be true. Why? Because every single value doesn't have to be satisfied. There just has to exist one value of x. So, well, clearly, at least one positive number exists in this universe of discourse, and we can use that as evidence that this statement is indeed true. While it is true for this case over here, it is false for this case because our universe of discourse includes negative numbers, and those are not satisfied. Remember, this one means that every single item in the warehouse has to satisfy px. So this right over here is false. Let's include a more complicated example. Alright, so this is a more complicated example, and this involves two different quantifiers. So what does this mean? This means that for all values of x, there exists at least one value of y such that our statement over here is true. So let's assign a meaning to this statement to make it more obvious and clear. Let's set p of xy to be equal to x plus y equals 0. So this is what the statement means. So let's retry this once again. For all values of x, there exists at least one value of y such that x plus y is equal to 0. Alright, so what does this statement really mean? this means that I can pick any value of x from my universe of discourse, and there will always exist at least one y value which satisfies this equation. So let's pick like a really random value for x, and let's go with 13.7. So this means if I add 13.7 with y, then there exists at least one value of y for which this statement is true. Does y exist? Well, yeah, y is negative 13.7, so this statement checks out. There does exist at least one y value that makes the statement true. But of course, again, you have to remember that this depends on the universe of discourse. If y's universe of discourse is the positive numbers, then it won't be true, because you can't add a positive number with a positive number to get 0. So in this warehouse of positive numbers, there won't exist a value which makes the statement true. You just can't add two numbers together which are both positive and end up with 0. That's just not gonna happen. So again, what this statement is trying to tell us highly depends on the context which surrounds this statement or the question or type of problem that we are dealing with. Now notice that the order also matters. So if I were to flip these around and say there exists a y such that all x values satisfy this equation, then we end up with a whole new different statement altogether. So what does this mean? This means that if we start with our statement over here, which is x plus y equals 0, then there will exist a value of y such that all x values make this equation true. Now, do you think that y value exists? Is there a y value that makes this equation true for all possible x values? Well, I don't think there is one. Like, let's say we pick a y value like 5 is equal to 0, then there's only one value of x that works, while this one asserts that all values of x should make the statement true. But it doesn't. Only one x value works. And, well, it's pretty obvious that you can't pick a specific y value to make this equation true. Like, even if y is 0, then, well, x has to be 0 as well, right? So this is only one value of x. Any other value of x, like 5 or something, will create a false statement. So it's just not gonna work. So notice that flipping the two orders of these quantifiers around drastically changes what you're trying to communicate. And actually that is all for this video, a pretty short one.